Greetings to all the attendees of the 5th edition of the EAI International Conference on Intelligent Transport Systems. It is a pleasure to be here presenting the research project entitled Enabling Citizen-Centric ITS Services Through Blockchain and Human Incentives, which has been developed by myself, Sofia Martins, as well as António Costa, Zafeiris Kokkinogenis, and Rosaldo Rossetti. This is a project of the Laboratory of Artificial Intelligence and Computer Science of the University of Porto. The motivation for our work stems from the fact that our mobility infrastructure has been experiencing several problems such as traffic congestion, noise and air pollution, which are a direct consequence of an increasing need for mobility in urban centers. These phenomena clearly contribute to the degradation of quality of life. Without applying significant measures to manage urban mobility, we can only expect this to worsen since more and more people will migrate to urban centers. In this sense, mobility regulation strategies can have several motivations, be it to reduce the carbon footprint, increase a country's revenue, reduce traffic congestion, noise, among others. There are two key concepts that we believe can help solving those issues. The first one is called Urban Vehicle Access Regulation, which encompasses various strategies that aim at regulating access of certain vehicles to specific areas in a city based on their class or purpose. In general, there is an underlying objective that characterizes and distinguishes these areas. In the left picture, we can see an example of an area in Barcelona, known as a low-emission zone, which is characterized by the objective of reducing carbon emissions. Other short or long-term objectives may be employed, like improving the attractiveness of urban and tourist centers. Several techniques and typologies have been adopted to implement urban vehicle access regulation, either by physical restriction of access, such as physical barriers or traffic signs, or through application of circulation charges in reserved areas. The charges may vary according to the time of day, distance or duration of journeys, or even the type of vehicle. In the case of the left picture, the traffic sign informs drivers that fines are enforced for some polluting vehicles entering the restricted low-emission zone. The right picture, on the other hand, illustrates the case where vehicles are charged for entering a restricted area in Milan. Those charges were called congestion charges, as main objective in this case is to keep traffic flowing properly in that Italian area. Now, we believe that gamification can be used as an urban vehicle access regulation strategy. The concept of gamification has been approached as a means of promoting engagement and behavior change, with positive and playful experiences in non-game contexts, like mobility. We can either opt for reward or punishment strategies. However, studies have shown that at least in the first phase, a reward strategy should be used to encourage pro-social behavior. In our work, we propose a blockchain-based system that attempts to influence drivers equipped with mobile phones during commutes to follow alternative routes rather than others that include roads with special characteristics that may be momentary, such as rush hour congestion, or persistent, such as those where efforts are made to reduce carbon dioxide emissions. We define those roads as exclusion roads. Different vehicles may coexist within our system. We consider, for example, the distinct roles of a typical passenger vehicle and an emergency vehicle. Clearly, the emergency vehicle should have indiscriminate access to any road, regardless of it being an exclusion road or not. The alternative routes may incur some degree of inconvenience for the driver, such as added commute time, so a proper incentive mechanism needs to be employed. The choice of a proper incentive should be managed by a municipality and could vary from monetary incentives to free tickets to access the city's public transportation system, which would also foster the city's sustainability patterns. The transaction of rewards is what motivates the adoption of blockchain. By relying on a distributed ledger technology, we guarantee transaction transparency. In addition, it makes it possible using smart contracts to check unequivocally whether the drivers hold to their commitment to follow the alternative routes when applicable. Our proposed architecture includes an Android app component, which is deployed at mobile devices that assist drivers. Drivers may register their vehicles through a membership service provider, or MSP, which is responsible for requesting to a certification authority, or CA, the public and private keys that uniquely identify the vehicle and prove its identity. Each vehicle is registered with the MSP through its license plate, which allows the MSP to derive a mapping of the cryptographic hashes generated from these license plates to the vehicle category. As a result, the MSP can easily recognize to which category each vehicle belongs. Upon registration of the license plate within the Android application, the driver may access its navigation mode and select an origin-destination pair for its upcoming trip. This is where the server comes in. At first, the server's REST API provides the list of available locations to the client application. After the driver has selected an origin-destination pair, the server submits the list of alternative routes, some of which may include exclusion roads, according to their momentary or persistent characteristics, which are properly monitored by the server. The set of routes that do not traverse any exclusion road is called a special proposal set and provide a means to influence the driver's route selection. As for the underlying blockchain network, what we can observe from the figure is that its architecture is similar to the one implemented by the Hyperledger Fabric framework. Once the server replies to the client app with a special proposal set, it also issues one transaction proposal for each of the routes included in the set through the SDK. Since the server is also registered with the MSP, the proposal is signed by the server using its private key. Upon this stage, the proposal enters the blockchain network and is passed to the orderer node, which asks the endorser peer to validate the server's key by consulting the MSP. If the proposal is successfully validated, meaning that the key is accepted, is recognized by the MSP and belongs to the server, then it is delivered to the client app through the SDK. Finally, if the driver accepts one of these proposals, its private key is used to sign the proposal and invoke the proper smart contract execution, which encapsulates the transaction conditions. Then, the orderer node initiates the validation of the last signature, and upon receiving the confirmation of the validity of the proposal, it generates a transaction block and delivers it to the general peers, which record it. Besides having proposed the blockchain-based architecture, we have also designed and implemented a proof of concept. The proof of concept was implemented using the simulation of urban mobility, which is an open-source traffic simulation package that enables us to individually model each vehicle and its dynamics. We have selected the city of Porto as our experimental scenario. You can actually see on the left picture this scenario on our simulated environment, which is based on OpenStreetMap. In addition, we have used the Traffic Control Interface API to manipulate simulated vehicles' behavior in real time. We considered a route between two well-known areas in the city of Porto, as well as an exclusion street. The setup of the proof of concept also includes a Python application. We employ it as a middleware between the traffic simulator and an emulated Android mobile device. The Python application acts as a logical unit to control the driver's decisions. In addition, it exchanges the vehicle's geolocation with the respective Android device, which mocks the Android device's location. In turn, the Android device executes an application that we have developed. This application allows drivers to either accept or reject route proposals as expected from a real-world deployment. For simplicity of the experiment, it takes on the role of the certification authority and the MSP that are part of the blockchain architecture. So the Python application has information about the classes of vehicles and restricted access zones, and as a result, it carries out class authentication of the vehicle, distinguishing between a private passenger vehicle and a priority emergency vehicle. Before initiating a new commute, the driver chooses an origin-destination pair and has the possibility to choose between two routes, one of which will avoid the exclusion zone, which is subject to an incentive. So the driver will receive a bonus by accepting the proposed alternative route and following it until reaching the preset destination. However, different conditions apply to emergency vehicles. When entering the exclusion zone, emergency vehicles will only receive a notification as navigational information, whereas passenger vehicles, which are encouraged to change their behavior, will receive a warning of breach of the proposed agreement. Now I'm going to show you the proof of concept running. On the left, we have the emulated Android application through which we have previously registered vehicle's license plate. At first, the driver selects the origin-destination pair that we have selected for our demonstration, and the Python application has recognized that the license plate provided belongs to a passenger vehicle, and has suggested that the driver selects the route that includes the street Praça da República and not Rua dos Clérigos, which is an exclusion road. So the driver has selected the alternative route through Praça da República, and now our mock GPS functionality is working, and we will be able to see the red vehicle moving on the simulated environment that is displayed on the right-hand side of the screen. So now the vehicle is going through Praça da República. And in this case, it has indeed complied with the agreement to follow the alternative route, so the application informs the driver that he has collected a reward. In this second experiment, we want to demonstrate what we expect to happen on a real deployment of the system. So we have preserved the previous conditions. A passenger vehicle selects a route from the special proposal set. However, in this case, the driver will not comply with the agreement. So as you can see, the driver is immediately informed that there has been a breach in the agreement, as he has already crossed the exclusion road, so the reward transaction will not be taking place. As a final note, I would like to recall that our work has focused on a strategy to promote behavioral change in order to encourage more sustainable practice in urban centers and to remove car traffic from the most sensitive areas. Our contributions are twofold. First, we have proposed a blockchain-based system that issues rewards to drivers who opt not to travel through exclusion roads. The motivation for using blockchain lies in improving transaction transparency and guaranteeing that drivers hold to their commitment. If that is the case, then they receive a reward. It is up to each municipality to manage the reward types. Secondly, we have designed and implemented a proof of concept, which relies on an urban mobility simulator. Our aim was to illustrate the client-level component of our system and pave the way for the accomplishment of our upcoming work. In this line of thought, future work will focus on the distributed ledger level components of the system through the development of an Hyperledger Fabric network operating through programmable smart contracts. In addition, we aim at employing our current experimental components, namely the simulator, the Python application, and the Android application, for evaluating the effectiveness of the system once all its components are fully implemented. For the interested attendee, you may refer to this slide for author contact information. Thank you very much for attending this presentation. If you have any questions, I'll be glad to answer them.